In this video, we're going to do some calculations related to weak acids and weak bases. We're going to take a look at how to calculate pHs, Kas, and Kbs. In the previous lesson that we've seen, we reviewed grade 11 acid-base concepts where we were dealing with strong acids and strong bases, and it was pretty straightforward to calculate pH and pOH from there. Here we're going to have to make use of the idea that weak acids and weak bases do not ionize or dissociate 100%. So we can't just take the concentration of the acid and equate it to the concentration of the H+, for example, because not all of the H from the acid will actually ionize to become H+. So we have to take that into consideration when we're doing our pH calculations. All formulas will essentially be the same. So if you're calculating pH, you need to do the negative log of H3O plus, pOH, the negative log of OH minus. The relationship between pH and pOH still is, when you add them together, you get 14. You can multiply your hydronium and hydroxide concentrations to get 1 times 10 to the power of negative 14. So all that still exists. It's just how we find the concentration of H3O plus and OH minus that will be different in the cases of weak acids and weak bases. So let's take a look at an example over here. We have a 0.200 mole per liter solution of HCN that has a pH of 4.95. What is the Ka of this solution? So first of all, you need to realize that HCN is not one of your strong acids. There's a couple ways you can do that. You can memorize a strong acid list that was mentioned in class, or you can also take a look at the Ka table over here. And if you look at the Ka table, you'll see anything that has a very large Ka, whether it's monoprotic or polyprotic, that would be considered a strong acid. But anything smaller that does not have very large next to it would be considered a weak acid. So if we look at HCN, hydrocyanic acid, we have 6.2 times 10 to the power of negative 10. That would be the Ka value if you were looking in your table. Now, we can't just go and grab the Ka value from the table for this question because we're asked to find what the Ka for this solution is. Maybe this isn't happening at SATP. It could be different conditions. So we need to find Ka. So here's what we're going to do. We're going to make a ice table because Ka is just an equilibrium constant for an acid. And in particular for weak acids, because they exist in that equilibrium that go back and forth. So let's go ahead and make our ionization equation, HCnAq. When we put it in water, it's going to react with water. Water's liquid. Don't forget to put liquid because we don't want to include it in our equilibrium expression. And since HCN is an acid, it's going to give an H away to H2O. So we're going to have Cn minus, and the reason it's Cn minus is because you lost an H, and so H was H plus, and so every H you lose gives you a negative charge. So we have Cn minus plus H3O plus. And the reason we have H3O plus is because the H from the HCN went to the water. And whenever you get an H, you get a positive charge because the H plus is a proton essentially. So now what we're going to do is we're going to make an ice table and plug in some data, which will help us figure out our Ka. So we'll have an ice table here. And assuming that we just put the acid in, we'd have 0 of this, 0 of this, and our change would be based on the molar coefficients, plus x, x, and x. If the coefficients were different, you might have 2x, 3x, so on and so forth, but right now it's just x and x. We don't really need to care about the water because the water is a liquid, its concentration won't be changing. And we have our initial concentration of HCN, which is 0.200 mole per liter. And that would be minus x. And so the equilibrium expression would be 0.200 minus x. Now, we can't say that x is equal to 0.200 because here's the thing. Not all of this H will ionize to become H3O plus. We don't know how much of that will occur because we have a weak acid. So in the strong acid situations, if I had 0.2 mole per liter HCN, I could automatically assume that I would have 0.2 mole per liter H3O plus because 100% of it ionized. And then I could just do my calculations that way. However, in this situation here, I can't assume that all of it ionizes. Only a small portion will, and that's going to be the X value here. So we want to find Ka. Remember that Ka is the equilibrium expression for this setup. So it's going to be the concentration of H3O plus, or you can write H plus for shorthand, times Cn minus over HCN. Remember, we don't include water because it is a liquid. So if we were to replace everything by the equilibrium values, expressions that we have here, we would get X times X over 0.200 minus X, which is X squared over 0.200 minus X, because X times X is X squared. So we want to find Ka, which basically means we need the X value. Okay, where does the X value come from? Well, think about this. You have the pH given to you. So we're going to do a little side step here. pH is equal to 4.95. Remember, the pH came from H3O plus. That pH is at equilibrium. So that essentially is what your X value is going to be. But you need the H3O plus concentration from pH. So if you want the concentration of H3O plus, remember the relationship is 10 to the negative pH. So in this situation here, that's 10 to the negative 4.95. So that's what my X value is going to be. This is 10 to the negative 4.95. This is 10 to the negative 4.95. And this over here is 0.200 minus 10 to the negative 4.95. So this is our X value based on what was given to us in the question. So now all we have to do is plug everything in and solve for Ka. So Ka is equal to 10 to the power of negative 4.95 squared over 0.200 minus 10 to the power of negative 4.95. And we get, so let's try this out in our calculator, 10 to the power of negative 4.95. Let's square that, divided by 0.200 minus 10 to the power of negative 4.95. And it's important that you try this in your calculator yourself because you need to get a sense of how your calculator works with the exponents. And we get 6.29498013 times 10 to the power of negative 10. Remember, there's no units because it's a Ka. It's an equilibrium constant. And so that's approximately to the correct number of sig figs, which is 3 sig figs, 6.29 times 10 to the power of negative 10. That is the Ka for this particular acid. Let's see how it compares to what's in the table. So in the table, we have about 6.2 times 10 to the power of negative 10. So that's pretty close. It might be just because we have some experimental error. It could be that it's a different condition, maybe not SATP, but it's pretty close to what we would expect for this situation here. So what did we do in this question? We had to find the Ka for this acid over here, which is a weak acid. We were given some information, the initial concentration of the acid, and then the pH, which is the pH you would measure at equilibrium. You wouldn't measure it before equilibrium because the pH continues to change. So you might monitor it, but you want to get your final measurement once equilibrium has been reached, so that way your pH is fairly consistent. And so we created an ice table where we had HCN in water becoming CN minus and H3O plus, and that indicates we have an acid. We put in all our data, our changes, and we just had to find, and we created an equilibrium expression. And so from that expression, we want to solve for Ka, but we needed the X value. And the X value came from the pH, which was given to us in the question, which you could use to find your H3O plus concentration, 10 to the negative pH. So then we plugged all that into our X values for our Ka expression, and we got this Ka over here, which we rounded to 3 significant figures because the smallest number of sig figs in this question was 3. So that is an example where you had to find the Ka of a solution. In the next video, we're going to take a look at how can you find the pH of a weak acid solution given the Ka.